Hi guys, in this video we're going to create a 95% confidence interval for the mean. Okay, so what am I saying? I want a 95% confidence interval for mu. Right, this is what we're getting. Right, the formula to get this, first of all, we have two conditions. If n is greater than or equal to 30. This is the kind of agreed upon cutoff point. Consider a large sample if n is greater than or equal to 30. Or if n is less than 30, or a small sample, we need some extra information. We know that the population distribution, so let me abbreviate as much as I can. We know that population distribution is approximately normal. So if one of these two things is satisfied, namely this guy, we have a sample size of at least 30, or if we don't, we have some extra information. We know something about the population distribution's shape, specifically that it's approximately normal. Then we can create a 95% confidence interval for mu using this method that I'm about to present. Now, this method is for the most realistic case, and that is when sigma, the population standard deviation, is unknown. That's the most realistic case. If sigma is known, we can use the z distribution in our method. But if sigma is unknown, which is much more realistic, sorry, I was trying to underline that, then we use this technique. So what is the technique? So here is the formula. So we first calculate x bar, and then we do plus and minus. So we have two calculations to do. The t critical value with degrees of freedom, a certain degrees of freedom, which we'll talk about, and a certain confidence level. Okay, for us that's going to be 95% for this example, times the sample standard deviation, which we can calculate from the data, divided by the square root of the sample size. Okay, so this is going to be our method. We're going to use the t distribution as our probability model, okay, to create a c% confidence interval for mu. C, let me mention, is the confidence level that you require. Okay, so this is the confidence level. For us in this example, we'll do at least one. We'll do 95% confidence, as I said. Degrees of freedom is something not unique to the t distribution, but for the t distribution, it's calculated by taking the sample size minus 1. Okay, and that once we have this and this, we can get the t value here. Okay, you can get that either from a t table, or I'll show you there's a way to get it directly in Excel with a function. All right. As for the rest of these components, x bar we're going to calculate together using a function Excel. Sample standard deviation, same thing. All right, so let's get to it. First, let's get x bar, or the sample mean, equals average. Highlight all the data. There's our average. Now we need the sample standard deviation, equals STD EV dot, there's two to choose from, dot S, that's sample standard deviation. The other one's population. And then you highlight all the values again. Okay, if I'm going a little fast, you can always pause and resume at your own pace. So we have these. Let's get rid of a few of these decimal places. Let's see, our confidence level is going to be 95, and we don't need to explicitly write that. let's get the sample size. We do need that. And unless you want to count it, use the function count in Excel. Highlight all the values of our sample. We have 40 observations. Okay, so now we can go about start to do the 95% confidence interval for mu. How did I get that? Hold the Alt key, type 230, you'll get the Greek letter mu. It's not terribly important to get that symbol, okay? But I just want you to see what I'm doing here. So we need the T critical value from the T distribution with degrees of freedom. So let me do underscore to indicate a subscript. Degrees of freedom here is going to be 39 degrees of freedom because n is 40 and it's 40 minus 1. And we have 0.95 level of confidence. So let's write those things explicitly. This is just n minus 1. And the confidence level that I chose for the first example at least is 95%. Okay? So let's get this. I'll show you how to get this T critical value equals T dot INV, open parentheses. If I want a 95% confidence interval, then I'm going to have 2.5% on the left, 2.5% on the right, and in the middle I'm going to have 95%. So the way I communicate to this function is to type 0.975. Okay, and let me actually draw this. Here's the T distribution, let's say with 39 degrees of freedom. Okay, centered at 0. I want a 95% confidence interval, so I want the middle 95%. All right, so we're going to get this number here, okay? And once we have this, by symmetry, we'll have this. So by drawing this picture, I want you to notice that 2.5% is going to be here. 2.5% is going to be here. Okay. Together, these three pieces I wrote here equal 100%, which should always be true. The way the Excel function works, and we have to adapt ourselves to it, is that in order to get this value over here, I have to give the cumulative percent of data, or proportion of data, or probability of data up to that point. So that's 2.5% plus 95%. So I communicate to Excel by writing 97.5, and it will give me this T value. Okay, so if you want, you can use your table as well. Okay, you'll look up 39 degrees of freedom and 95% confidence. Comma, degrees of freedom, we have this over here. Okay, close parentheses, hit enter, and this gives us a lot more detail than the table will. Okay, so now we can compute the confidence interval. So let's do lower bound first, and then upper bound, because a confidence interval has a lower bound and an upper bound, right? So in the lower bound, let's do equals. Remember the formula I had up. X bar minus, and then the T critical value we just calculated, times, in parentheses, S divided by the square root, that's how you do square root, of the sample size. So close the square root function, close the fraction parentheses. Let's double check our parentheses match up, hit enter. That is the lower bound of our confidence interval. Okay, and now we go through a similar process with one difference to get the upper bound. Equals X bar again, this time plus instead of minus, the T critical value times parentheses, S divided by the square root of the sample size, close parentheses, hit enter. This is our 95% confidence interval for mu. Okay, by the way, we can do this problem because the sample size is considered large, right? That was one of the conditions. Now, it might not be a bad idea, now that we're on a roll, to get the 99% confidence interval for mu and see if there's any interesting difference to notice. Okay, so here I'm going to have t. I have to get a new t value. Everything else stays the same. The confidence level is the only thing that changed here. It went from 95 to 99. So I still have 39 degrees of freedom, and I still, and yet this time I have 0.99 for my C value, right? So let me erase that because this changed. We have two different confidence intervals we're calculating here. So I need to get a new t value. So equals t dot inv, and if you followed the logic before, here's the t distribution again, a little uglier than last time, with 39 degrees of freedom. Okay, here's 0. If I want to get this middle 99%, okay, then 0.5% is of observations are there, and 0.5% of the observations are above this. So up to this point, so what do I mean by up to? From all the way from negative infinity up to this value that we want to get, this t critical value, is 99.5. That's this plus this. So that's what I'm going to feed in to Excel. 0.995, comma, 39 degrees of freedom. That didn't change. Hit enter. Okay, that's our critical value. And then our computation for the upper and lower bounds are going to follow very similarly. X bar minus first, t critical value times S divided by the square root of the sample size, and the upper bound equals X bar plus this time t times parentheses S divided by SQRT, open parentheses, sample size, close, close. And now we have the 99% confidence interval for mu. So what are these confidence intervals saying, first of all? So let's just take this first one. If we were, what this is the most technically correct way to say, what does this interval mean? If we were to repeat, if we were to take samples of size 40 over and over and over and over and over and over and over again, random samples, okay, from this population that this data came from. Remember, this is a sample. Samples come from populations. So if we were to take random samples of this specific size over and over and over again until we had every possible sample of this specific size 40 from this population, and each time we took a sample, we not only computed X bar, not only computed sample standard deviation, but also went ahead and created a 95% confidence interval, we would end up with many different confidence intervals, one for each sample that we collected. What this method is saying is that 95%, approximately, let's say, 95% of those confidence intervals will capture the true mean, which is mu. The true mean meaning the population mean. Okay, approximately 5% error rate. 5% of the confidence intervals that we would create would actually not capture mu, meaning mu would not be between these two numbers for only 5% of the time. Okay, So it does have a 5% error rate. All right. So that's what this method ensures. Now let's look at the numbers. So mu. So this confidence interval is from 20.481 to 22.574. Now, in order to be 99% confident, that means I want to be more confident that I'm capturing mu, and nothing else changed. I end up making an interval that is slightly but noticeably wider. And actually, a more technical word is less specific. Okay? Because it's wider, it's more vague. Notice this number is lower than this number, and this number is larger than this number. This interval is wider than this interval. Okay? So in order to be more confident, everything else remaining the same, that is, I have to say something less specific. In terms of numbers, that means I have to make a wider interval. Okay? So more confident and less specific. Less confident, more specific. Okay? So the idea is, if you wanted to be more confident and not become wider, then you can increase your sample size. So this is an idea that is discussed in statistics, that taking a larger sample size is always going to yield more reliable information. And I think that is intuitively understandable. Okay? So I hope this was helpful on some level. Make sure to subscribe and check out the other hundreds of stats Excel videos I have on my channel. Like, comment. Until next time, have a great day.